All right. Our next speaker this afternoon is Tiffany Liou, who is joining us from UC San Diego. And Tiffany has been working this summer with Josh, and today she'll tell us about their project together, measuring dark matter with stellar streams.
Yes, so thank you, Gwen, and thank you everyone for coming. I'm really excited to share with you all what I found this summer about dark matter and stellar streams. So first of all, let me get into some background knowledge about what we know so far about dark matter. So first of all, dark matter is a really hard object to study. One, because we can't see it, and second, because it only interacts gravitationally. So currently, the most popular or most favored model for dark matter is called cold dark matter. So essentially, that means that the dark matter particles are very massive and they are non-relativistic. And so essentially, if dark matter is cold, then they will gravitationally clump into clusters called dark matter subhalos. And currently, the two most popular ways to test this model is through gravitational lensing, which deals with cold dark matter on more galactic scales, and also stellar streams, which focuses on more like localized scales, so smaller subhalos essentially. So what can stellar streams tell us? Well, first, stellar streams are basically the remnants of globular clusters or dwarf galaxies that are ripped apart by tidal forces by massive objects such as our Milky Way. And so this causes them to be extremely sensitive to any changes in gravitational potential. So any other massive object that flies past it might just change the trajectory of the streams itself. And because they are extremely sensitive, this provides a very unique opportunity to study dark matter substructures because, as I mentioned before, dark matter only interacts gravitationally. And so this summer, my project focused on two streams, which are GD1 and Palomar 5. And this is because they are the most prominent, longest, and thinnest streams in our northern sky. And this is extremely beneficial for us to study because the thinner the streams are, the more sensitive they are to perturbations in the stream. And moreover, another motivation to study these two streams in particular is that previous studies have showed that they are very sensitive to perturbations, and in fact, they also show features that indicate that they might have interacted with dark matter subhalos before. And one of these studies come from Anna's paper in 2019, in her paper on Palomar 5. So in this figure on the right here, there is basically a model data, so a simulated model, and that is being compared to the blue line, which is the observational data. So if we look at the second panel, the x-axis is phi1, which is kind of the latitude of the stream, and also phi2, which is the longitude of the stream. So essentially, these are coordinates. So as you can see, although the stream positions are relatively matching with each other, the other components and features of the stream do not, such as in the third and fourth panel here. So this one is the surface density of Palomar 5, and as you can see, there exists gaps in the density in the real stream that do not show up in the simulations, and also the same with the stream width of the stream. So essentially, the big problem is that the simulations do not match up with the observational data. And this essentially happens, this wouldn't happen without any gravitational perturbations. And the hypothesis here is that these streams, perturbations, might be caused by dark matter subhalos. And so this all boils down to the question of what stream features can be used to confirm the existence of dark matter, and also learn about the properties. Well, to answer this question, I will be looking at n-body simulations made by Dennis Ercole, and it is based on the real characteristics and the locations of GD1 and Palomar 5 streams. So this simulation has three different simulations of different subhalo populations. So the first one is no structure at all, which means that there are no dark matter subhalos. However, there are dark matter particles that are evenly distributed, not evenly distributed, but more smoothly distributed throughout the stream. And the second one is called lambda cold dark matter, which has the expected amount of dark matter subhalos populated in the universe. And the last one is the 3 times cold dark matter simulation, which is exaggerated with 3 times the amount of substructure that we would expect. And so in this simulation, the dark matter subhalos basically pass through the streams at randomized location and times. And so for this presentation, I will be presenting basically the most contrasting amount of stronger interactions to the streams. So namely Palomar 5, LCDM2, which has like the normal amount of dark matter expected, and also the 3 times the amount. And for GD1, I will present a lambda cold dark matter 1 simulation. And so stronger interactions basically come from higher mass subhalos, and we identify that to be 10 to the 7 solar masses or greater, and also subhalos that causes the largest velocity kicks, which is more than 0.5 kilometers seconds to the stream. And what this means is essentially the greater change in velocity. So the kick velocity is proportional to the mass and inversely proportional to the impact parameter. So if the subhalo is bigger, then that might cause a stronger interaction. And if the distance to the subhalo is smaller, then the velocity kick increases. And so here, if I'm looking at Palomar 5, some possible indicators of dark matter perturbations I will be looking at includes any density gaps, velocity dispersions, variations in stream width, and stream positions. So for the case of Palomar 5, we will be looking at the pink line, which is the 3 times lambda cold dark matter simulation. And this is just because it's the most prominent to see here. And so in the simulation, we kind of expected a density gap to occur where the subhalo passes. And in that case, it would be around this region, around centered around -50 degrees. And we can see that the density kind of dips down in this region. And so the density is in log scale. So as you can see, compared to the higher peaks in the stream, the density decreases by a factor of 10, which is pretty significant since it's like almost 0 density in that region. And so because this is such a big range of dips, ranging around like 50 degrees total, and it's also a very staggering decrease, we expect this to come from a higher kick velocity, which also lines up with the long peak in velocity dispersion in the same region over here. And continuing on with that, in this same region, we also expect this to correspond to an increase in stream width, which we also see in the same region. This is basically because as the subhalo passes by, the subhalo's gravitational potential energy transforms into the stream's kinetic energy. So essentially the stars, they gain velocity, and so they spread further apart from each other, which causes this huge deviation in stream width. Now in comparison to Palomar 5, GD1 is a little bit different. So there are 2 density gaps, as you can see over here. However, if we look at the density scale, this is a little bit different. Instead of a log scale, this is a linear scale. So even though we see that the gaps are there, it's still relatively dense compared to the other simulation. And so nothing much has changed for the stream width itself. And so we asked ourselves, well, why is there such little change in the stream width? And this all goes back to kind of the amount of strong interactions faced. So in comparison to Palomar 5, which has more than 1 strong interactions for both simulations, GD1 only had 1 strong interaction from one subhalo over the course of the entire runtime, which was about 5 gigayears for the simulation. And so in this sense, we asked ourselves, well, which dark matter interactions actually matter in the stream? So when we're looking at Palomar 5 and GD1, we notice that the most noticeable changes in stream properties occur only when there are larger amounts of interactions. And here I kind of just have a refresher of what strong interactions mean. And we can see that in Palomar 5, because the 3 times lambda CD amount simulation has the most strong interactions, we can see that it has more dips and it's more drastic than the lambda cold dark matter simulation or the one with no substructure. Yes, so as aforementioned, the 3 times LCDM1 model is exaggerated with 3 times the amount of cold dark matter populations. Future works might be creating more realistic parameters, and this is extremely useful because if we were to match a simulation to observational data, then we can see whether or not a subhalo actually passed through in the past or not. And yes, and another thing that will be useful to work on is continue quantitatively comparing different dark matter interactions. And this is just because it would be more helpful for creating a mass function in the future. So it'd be really good to quantify maybe the percentage of change that each subhalo causes to the stream, or how many degrees in like dispersions that the subhalos causes per stream. And so kind of to conclude everything, we found that in my study that density gaps coinciding with an increase in velocity dispersion and an increase in stream width are very likely features of dark matter interactions with stellar streams, and also that the number of strong interactions determine the changes in stream features. So this will be very helpful for future analysis. So yeah, thank you.
All right, very nice. Questions for Tiffany?
Hi, Tiffany. Wonderful talk. I don't know much about dark matter, so apologies if this is a bit misinformed. However, I was wondering if there were any plans to look at these stellar streams and subhalos with different models of dark matter, such as warm dark matter. If so, do you expect anything to be different? If so, what? Or is just using cold dark matter sufficient?
Yeah, okay, so that's a really great question, and why my project also focuses on cold dark matter rather than warm dark matter. So warm dark matter would be different because it's relativistic, so it kind of moves a lot and it's smaller in particles. So I'm not quite sure if warm dark matter would kind of cluster into clumps called subhalos, because I think subhalos only occur when cold dark matter, for the cold dark matter model. So yeah, I'm not sure how much warm dark matter will perturb the streams. So yeah, that answers your question.
Other questions?
I was just curious if you knew between the models why we choose 3 times for the lambda cold dark.
Yeah, so that's a really good question. So first, I will mention that the 3 times cold dark matter model is totally not realistic at all. It is exaggerated, and I believe it was just because it's easier to see like the differences in the streams. So maybe in this graph right here, I basically plotted all of the simulations on Palomar 5 that I have in like a 3D plotting kind of tool. And so the 3 times lambda cold dark matter one, you can see it's like one of the longer streams. And so the features are kind of exaggerated a little bit more, and I assume that it's just for analysis reasons, since I was doing this mostly qualitatively.
Yeah, thank you.
Other questions for Tiffany?
Yeah, so looking at your graphs, so is it safe to say that one dark matter subhalo corresponds to one of these like perturbations found per stellar stream, or can there be 2 dark matter subhalos that cause only one sort of this, only one of these features?
Yeah, so that's also a really good question. So I'm going back to the Palomar 5 density graphs. So as you can see, like in this region, this entire gap spans about 50 degrees. And in a paper by Dennis Ercol, he actually found that one dark matter subhalo, or like one strong interaction, causes around like 9 degrees of like the length of the gap. And this one, since it's like spanning 50 degrees, it must be coming from more than one subhalo. But at what times they interacted, I'm not sure about that. But yeah, it is definitely possible that more than one subhalo interact with the stream at once.
All right, let's thank Tiffany again.